Today we're going to look at applying vectors to do some geometric proofs, looking at different properties of geometry and how we can use vectors and certain properties of vectors to solve proofs. So, Euclid's first postulate states that a straight line can be drawn between any 2 points. So if we're looking at all of these different types of drawings using lines, each of them has a different property. So quadrilaterals are sort of your base level. You should all know this. A plane four-sided figure with no sides necessarily parallel or equal. Trapezium, we have one pair of sides parallel but not equal. So when looking at that through the lens of vectors, AB is going to be parallel to DC, and we know that two vectors that are parallel are just scalar multiples of each other. So AB is equal to K times DC. For a parallelogram, it's very similar. We've got a plane four-sided figure with two sets of side parallel, but now we also have them equal in length. So instead of just being a scalar multiple of each other, they are indeed exactly equal. Then we have a rectangle with all angles 90 degrees. So if we were looking at AB dot product with BC, because the angle between them is 90 degrees, that's going to give us 0. A rhombus is a parallelogram with all sides equal, and a square is a rhombus with all angles 90 degrees. So let's take a look at proving that if the diagonals of a parallelogram are equal in length, then the parallelogram must be a rectangle. So where do we start? We have these two vectors here. We've got that O to A is the vector A, and O to C is the vector C. If we express the diagonals in terms of the vectors A and C, we can see that O to B is going to equal A plus C, and A to C is going to be minus A plus C. And we want to determine that these two diagonals are equal in length. So assume that the magnitudes of these two are equal. So if we know that, what can we do with that? Well, a property about the magnitude is that the square of the magnitude can be found using the dot product. So if we square both sides of these, we can use the fact that the square of the magnitude is just the vector dot product with itself. So this becomes OB dot OB, and this becomes AC dot AC. So what does that give us? That gives us A plus C dot A plus C is equal to minus A plus C dot minus A plus C. So if we then distribute these, what do we get? Well, we get A dot A, we get two lots of A dot C. This is just binomial expansion. And then C dot C. And we've got on the right-hand side, negative A dot negative A. We've got minus 2A dot C. And we have plus C dot C. So we can see we've got some cancellation happening here. So if I were to cancel the C dot C as well as the A dot A, so because regardless of the direction of the vector, if you take the dot product with itself, it's going to be twice the magnitude. So the direction doesn't matter. So negative A dot negative A is the same as A dot A. So these two cancel. and C dot C and C dot C cancel. So we get that 4 times A dot C is equal to 0. We can divide both sides by 4 to show that A dot C is equal to 0, which means A and C are perpendicular. Therefore, the parallelogram is a rectangle. All right, let's take a look at the next example. So given the points D, 6, 1, negative 3, E, 2, 3, negative 4, and F, 5, 7, negative 8, prove that DEF forms a right-angled triangle at E, and hence calculate the area of the triangle. So let's convert these points into vectors. D is going to be the same as let's call it O to D. So O to D is the vector 6i plus 1j, or just j, minus 3k. Then we've got O to E, which is 2i plus 3j minus 4k. And then we have O to F, which is 5i plus 7j minus 8k. So what can we do with this? Well, what we're wanting to find is that the triangle has a right angle at E. So what we want to show, that DE dot EF is equal to 0. So let's first get these two vectors. So D to E is going to be the same as OE take OD. And that is going to give us negative 4i plus 2j minus k. And then E to F is going to be O to F take O to E, which is going to give us 3i plus 4j minus 4k. Okay, now that we have these two properties, we need to take, these two vectors, we want to take the dot product and show that they are indeed perpendicular. So DE dot EF is going to give us negative 4 times 3 plus negative 2 times 4 plus negative 1 times negative 4. That's going to be negative 12. What have I done wrong here? This should be positive 2j. That's what I've done. So we've got negative 12 plus 8 plus 4, which is going to indeed give us 0. Sorry for that small error there. So therefore, DE is perpendicular to EF. Now we need to find the area of the triangle. So we can use the fact that its area equals half base times height. In this case, B, the base, because the right angle is at E, the base length can be given as the magnitude of the vector DE, and the height can be given as the magnitude of the vector EF. And so the two magnitudes of those are square root of 21 and square root of 41. So if we multiply those together, we get that the area is half times square root 861. And we'll say units squared. Okay, there's a nice image in the textbook that sort of illustrates this in the 3D plane. I'll probably just copy and paste that into the OneNote at a later date so that you guys can have a look at that. Let's move on to the last example for today, I believe. Yep, last example. So a tetrahedron is defined by the vertices O, L, M, and N. Given that OL is defined by the vector L, OM is defined by the vector M, and ON is defined by the vector N, express L to M in terms of L, M, or N, express M to N, and express L to N, and then develop an expression for the line joining the midpoints of OL to LN. So let's start here with L to M. So if I'm starting at this point and I want to get up to here, how am I going to do it? Well, I need to travel back through L to O, and then I need to travel from O to M. So how are these defined? Well, that's going to be negative L plus M. So that is our vector for LM. Part B, how am I getting from M to N? Well, I need to go back through M. So M to N is equal to negative M, right? Because I'm going towards the left, and then positive N, because we're going up from O to N. And then part C, express Ln. So to get from L to N, I have to go back through L, so negative L. Sorry, let's define our vector, Ln. So back through L, so negative L going in the opposite direction, and then upwards through N. So using these three, we need to develop an expression for the line joining the midpoints of OL to LN. So let's take a look at that. So we've got a midpoint here, and we have a midpoint here, and we want to find an expression for the line joining these two. So let's define these 2 points. We're going to call P the point between O and L, and we're going to call Q the point between L and N. So O to P is parallel to L, and it's going to be half its magnitude. So we know OP is equal to half times L. OQ is the vector sum of OL and half of LN. Right, so O to Q, we're going from O to L plus half of L to N, both of which we have defined in terms of vectors. So that is L plus a half, and L to N we know is negative L plus N. So how do we find the line PQ? Well, that's going to be PQ is equal to OQ take OP, both of which have now been defined by L's and N's. So OQ is L plus 1/2 negative L plus N. We could have simplified it at the last step, but we might as well do it now. And then we're subtracting half L. So we've got L, take half L, take half L. That's going to be 0. So we're left with just half of the vector N. So if we go back up to this image, the vector N is coming up with this direction. And we can see that the vector P to Q is actually parallel. And more than that, it's not just parallel, it has the same magnitude. So if it's parallel and has the same magnitude, we can see visually that these vectors are equal. But now we've proved that using mathematics. All right, that's all for this video. Thank you very much for watching.